Hi there, my name is Aaron Lanterman, and today I would like to talk about wave-shaping synthesis, in particular what kind of sounds we could make if we use complex numbers instead of regular real numbers. In wave-shaping synthesis, you take one waveform, usually a sinusoid, but it could be something else, here represented as an X, and you pass it through a memoryless nonlinearity, here represented as the letter F. Before you do so, you multiply it by an amplitude scaling function, and by changing the amplitude of the input waveform over time, you get varying spectra. There's different ways to define F, but it's often convenient to define it in terms of polynomials, particularly if your input is a sinusoid. It's particularly convenient to specify your polynomial nonlinearity in terms of sums of Chebychev polynomials. If you take a cosine that has unit amplitude, so it's going between -1 and 1, and you pass it through a Chebychev polynomial of order n, you get a cosine out that also has unit amplitude, but it has frequency that's n times whatever the input frequency is. So by multiplying these Chebychev polynomials by some coefficients, you can create a polynomial where if you put in a cosine, and I should clarify a unit amplitude cosine, you get out a waveform that has spectra for a sawtooth or a square wave or whatever kind of waveform you might want. And then as you vary the amplitude going in, you'll get all kinds of other weird spectral effects. Now, to do wave shaping with complex numbers, I'm going to use Euler's formula. So you're used to exponential functions like growing populations or discharging capacitors, but if you take e to a complex power, what you get out are sinusoids. The real part is a cosine and the imaginary part is a sine. So if I take the real part of a complex exponential, I get a cosine. And that makes it really convenient for wave shaping, because if I take that complex exponential, that complex sinusoid, to the power of n, the n just basically goes inside the power here. And then when I take the real part of that, I'll get a cosine of that original frequency times n. So in order to get a cosine of a certain frequency out, all I need to do is just take a power. I don't need to mess around with Chebychev polynomials. So I wrote some MATLAB code to play around with this. As usual, I'm actually running this in the free Octave, so you can try out the code yourself without having to spend a lot of money on a MATLAB license, and I'll include the code in the description below. So I would encourage you to download my code and play around with it. Anyway, before I go through the details of the code, let me play a few examples. First, we'll explore a square wave. And what I'm going to do is I'm going to have an envelope that ramps up, and then we'll briefly hear the harmonics of the square wave, and then it will promptly ramp back down. And in each example, what you're going to hear first is going to be the result of usual real-valued, real sinusoid wave shaping with Chebychev polynomials, and the second thing you hear is going to be the complex number version. I should also mention I'm restricting our analysis to the first 32 harmonics to avoid aliasing. So that targeted square wave harmonics when we were at the peak. Now we will look at sawtooth harmonics, and I should emphasize this is Sawtooth-sounding because we're using cosines. If you think about the Fourier series for a cosine, that's going to produce odd waveforms, and the sawtooth is an even waveform. So to actually create a sawtooth shape, we would need to use a sine series. Anyway, as far as what you hear, it's going to sound like a sawtooth, even though the wave shape won't look the same. And this is the example I started the video with. Notice that for traditional wave shaping based on real cosines, we have kind of this swirly sound where different harmonics are fading in and out, whereas with the complex number version, things fade in and then they just fade back out without that swirliness. The qualitative behavior reminded me of some of my experiments with FM synthesis with complex numbers, where traditional real-valued FM synthesis results in some swirly sounds resulting from Bessel functions fading in and out, whereas the complex number version invokes modified Bessel functions, which are monotonic. Also note I haven't put any additional amplitude envelopes on the output, so you will sometimes hear clicks at the beginning and end of an example. And as you might guess from these time domain plots, wave shaping synthesis can have an issue with DC offsets, so in practice you might want to put some sort of high-pass filter that's set to a low frequency to block DC. Okay, let's do another example. Here I've set all 32 harmonics to be the same amplitude, so this should give us an impulse train at the peak. Something crazy happens right here. Okay, now I've set all of the amplitudes to be the same for the odd harmonics, but the even harmonics are 0. So this will give us a bipolar impulse train. Okay, one more just for fun. This corresponds to a Hammond organ where all of the drawbars have been pulled out. Okay, let's talk about code. If you've seen some of my other recent videos on digital synthesis, this will look familiar. I'm using a sample rate of 48 kilohertz. I'm creating a set of time values for 10 seconds of signal. For all of the examples I've played, I've set the frequency to 110 hertz. This O here stands for omega, so I'm multiplying by 2 pi to get the frequency in radians per second that I can use later on. So here I'm letting B represent my harmonic amplitudes, so you can select whatever line you want or make your own line. A is my amplitude envelope, so I'm using linspace to ramp up from 0 to 1 and then back down. So for a lot of the variables here, I'm using underscore complex or underscore real to indicate which version of wave shaping we're doing for a particular kind of variable. So I'm using xn to represent the unit amplitude input sinusoid. That's either a real cosine or one of these complex exponential sinusoids. And I'm an electrical engineer, so I like to use j for the unit imaginary number of square root of -1 instead of I. I multiply those sinusoids by a, my envelope, to get these xx envelope variables. Here I'm using MATLAB zeros command to initialize some variables that I'm going to use to sum up the results. I'm using this recursive definition of the Chebychev polynomials, where t0 is equal to 1, t1 is equal to x, and we have this definition of the other Chebychev polynomials in terms of the two previous polynomials. So here I'm kicking off the recurrence relationship by setting what I've called chebyprev equal to x and chebyprevprev equal to 1. So this is t0 and this is t1. In this loop that I have here, you'll see that I'm declaring my new Cheby result to be equal to 2 times x times the previous Chebychev polynomial minus the previous Chebychev polynomial. So this is that recurrence relation. I take the output of that Chebychev calculation, multiply it by my harmonic, and then add that to what I'm summing up. And then I do a couple of lines here in order to move everything forward and get it ready for the next iteration through the loop. I have a similar kind of calculation for the complex number stuff, but here it's a lot easier. So my first power is just xx, and then each time I run through the loop, I just multiply that power by xx to get the next power. And then for the sum for that loop, well, I can just take that power and multiply it by my harmonic amplitude. Notice that I started this for loop at 2, so I have a couple of lines here to manually handle the first term. Now, before I start plotting or playing any sounds, I need to take the real part of my complex result. Notice I'm still calling it complex because it's the result of all these complex value calculations, but at this point, this is now a real value. Something I want to warn you about is that the sound SC command needs you to put 16 here for 16 bits, otherwise it defaults to 8 bits. That really messed me up on a previous video. So hopefully that gives you enough of a roadmap that if you want to start modifying my code and playing around with it, you will have a place to start. If you're new to MATLAB, the one thing you want to watch out for is that you want to put a period in front of, say, the asterisk here to do multiplication. Having that period there means that you'll get element-wise multiplication instead of some matrix multiplication. Same thing with the kind of divide that you see here. Before we close out, let's do a little math and try to figure out why the complex number version of Waveshaping seems to produce more predictable results than the real valued version with the Chebychev polynomials. So I've just made some space here so I can think out loud a little bit. So let's take this XX envelope complex, paste it here, and let me take this complex exponential and paste it in here. And if we think about what our results are, well, we're really going to be summing over all of our various harmonics. So let me write this something like sum over n, and I'm going to have b of n here times this form here to the power of n. So if I take this n and distribute it through, well, I'll have a to the n in front here, and then the n goes inside here like this. So for each of my harmonics, the amplitude is a monotonic function of a. That's not something we get really very often with the Chebychev polynomials. So this gives it a more predictable behavior. And notice that if I were to decrease a, say between 1 and 0, then the higher order harmonics wind up decaying faster than the lower order harmonics, which is a thing that a lot of instruments naturally do. This reminded me of some of the work with discrete summation formulas we looked at around a month ago, so I'm wondering if this all is somehow related. Let's do one more example. This time a sawtooth type of sound with 64 harmonics and with a fundamental frequency of 55 Hertz instead of 110 like earlier.